Hi, this is Rob from Engineers Academy. As engineers, some of the tasks we are required to do may include designing, developing, testing, repairing, improving, troubleshooting, or maintaining products, equipment, or processes. All of these tasks require us to make informed decisions. To enable us to make good decisions, we need to be able to separate facts from simple opinions. In this video tutorial, we're going to look at the scientific methods used for examining data. Now, while it's called scientific methods, they do also apply to mathematics and engineering, since these are standard procedures that can be used to explore our observations, answer our questions, and solve our problems. Scientific method is a structured framework that consists of 6 basic steps. Doing our day-to-day jobs as engineers, we often come up with questions that need answers. If the questions are specific and measurable, it can be something that we could try and answer through some experimentation to get a real solution to our problems. So what we may ask is things like, why has the colour of a material started to change? Or would using another material be just as strong? Why has a machine started to make unusual noises? Or why we're getting more customer complaints for our products? So asking a question is the first step of our scientific method. To progress with answering the question, it is important to understand the current position we have surrounding the topic of our question. By doing some research, we can better understand what is already known, and therefore we have a better chance of avoiding and repeating any mistakes that have been made in the past. So the second step of our scientific method is research. Once we have a question and we have background knowledge on the topic, we might want to move further on and make some educated assumptions or form ideas or thoughts about what could help answer that question. So we might make an assumption or have an idea about how something works or what is happening. If we can predict an outcome from this, we will have a hypothesis. This is something that we can test with experiments to show if it is right and holds true or if it is incorrect. If we think our machine is making unusual noises because the bearings are getting too hot, this could be a hypothesis. Another one might be that if we use a new lubricant, it would flow better than the existing lubricant. Or we may find that we're getting a lot of customer complaints because one of our parts breaks more frequently than it used to. We might get a hypothesis that the material we're being supplied for these parts is not correct and that the wrong grade of steel is being used. This is something we could test. Developing our hypothesis is the third step of the scientific method. Once we've got our hypothesis, we need to develop and conduct an experiment that will test our hypothesis. Any experiments should be controlled and measurable, and data should be obtained from them. Running experiments is the fourth step of our scientific method. The fifth step of our scientific method is to analyse data that we've collected. We use data analysis or statistical analysis to draw conclusions from the data that will uphold or disprove the hypothesis that we have. Finally, in our scientific method, we need to draw conclusions from the analysis. We need to conclude if the analysis of the data supports our hypothesis. If it doesn't, we may have to rethink and come up with another hypothesis that we can test to see if there is another answer to our question. Once we're happy that we have a satisfactory answer to our question that is supported by science, we can form our conclusions, and then we have to communicate our results and our findings. Conclusion and communication is the last step of our scientific method. When we think about the types of data that we'll be using, we can consider it as coming in two forms. There's quantitative data and qualitative data. Quantitative data tends to be numerical or statistical information. More commonly, we just refer to it as data. An easy way to remember quantitative data is that it refers to a quantity or a number. Qualitative data doesn't have a quantity, instead it has a quality, and qualities can be observed or described. Qualitative data tends to be descriptive or observed information, and we'll take a look at this a bit later on. On the screen here we have a snippet of data from a UTS test. We can see the left-hand column is force, the second column we have a distance or displacement, and then we have stress and strain in the last two columns. Now it should be clear from looking at this data that what we have is quantitative data because it has quantities, it has numbers. So what we're looking at is an example of quantitative data. We can consider this type of quantitative data obtained from an experiment using an ultimate tensile test machine and relate it to our scientific method, where we could use this data to support or disprove a hypothesis such as steel has higher tensile strength than brass, or maybe brass is more elastic than steel. Or perhaps we might consider something more simple, such as the two tested materials are not the same because they have different tensile test properties. We could only come to these conclusions after appropriately analysing our data. On the screen here we have 3 test pieces that have undergone the ultimate tensile strength test. We can use this data as qualitative data because we can look at the qualities of the test sample to infer or draw conclusions from what we can see. The 3 samples from left to right are steel, brass and bronze. By examining the breakage areas on each of the test pieces, we can gather some information that isn't quantitative because it doesn't have numbers, but it is qualitative. So for example, looking at the sample on the right hand side, we can see that the fracture is clean without any stretching before failure. It's not got what we would call necking. This brittle fracture would indicate that the material is very brittle, where it has suddenly snapped without stretching beforehand. The other 2 samples show what we would call ductile failure, where they neck or stretch having a plastic zone where the material is pulled out and before it finally snaps. So the qualitative data here would indicate that the right hand sample is brittle and the other 2 samples on the left hand side are more ductile. We can also see that because of the necking before failure on the 2 left hand samples, that they're going to have more plasticity or be more plastic in nature than the one on the right hand side, which is obviously going to be quite brittle. In addition to the observed properties, we can also infer some deduced properties from these tests. Malleability and ductility go hand in hand. Most materials that are ductile are also malleable. However, ductility is a tensile property from stretching, and malleability is a compressive property from squashing. Although they go hand in hand, we can infer that it is likely to be malleable, the material, because it's ductile, but we can't categorically say because this is a tensile test and not a compressive test. Likewise, we can also infer that brittle materials are likely to be hard, but we don't know this for sure because we'd have to do an additional hardness test to confirm this. And we can also infer toughness as well, because plastic materials tend to be tougher than brittle materials. In addition to analysing qualitative data from our experimentation to confirm our hypothesis, qualitative data can be used in the research. There are many qualitative research methodologies and methods that can be used by engineers. But here we're just going to look at 2 methods in particular: customer product reviews and stakeholder interviews. I'm sure you're all familiar with customer product reviews, where we've used Amazon or a similar online purchasing website to buy a product. We go to the review section and we look at the product reviews before we purchase. These product reviews can be useful as an indicator. They can provide insights into product quality and performance. However, they lack detail, they're inconsistent, and they have the potential for bias and manipulation. So we can often use them as an indicator of what's going on, but we need to do further investigation to get more detail before we can progress with any certainty. Another qualitative research resource is stakeholder interviews. Stakeholders are many and varied. They include suppliers, customers, workers, and the general public. As part of an investigation into a quality issue on a manufacturing shop floor, an engineer might go and interview the machine operators to find out if they can shed any light onto the source of the problem. This would be an example of a stakeholder interview. This type of interview can be a good indicator into the direction of the problem. It can provide a rich source of data because usually the interviewees are honest and candid with their information. However, information can be inconsistent. It has a potential for bias and manipulation, and it is limited in sample size. So again, Any information provided would require some kind of further follow-up with some deeper data analysis. Where our quantitative data is in the form of a count, such as number of machines breaking down in a week by machine type, or number of vehicles passing by color type, this frequency data can be used to provide a visual output in the form of a Pareto analysis. A Pareto chart is basically a histogram of the occurrence of frequency arranged in the order of the largest to the smallest, as we can see here. It is useful to provide a visual indicator from a big list of numbers that makes it more simplified so we can provide an analysis of a direction in which we need to investigate. This is a process often used by engineers for some very basic data analysis of, for example, reject rates or product quality issues. A Pareto analysis is a useful indicator. It provides a good visual overview. We can draw from it the number of times an incident has occurred in the order of the most frequent occurrence, with a visual indication as shown. However, the data is often oversimplified, and the focus tends to be on frequency over severity. So, for example, if we were analysing the number of times a machine's broken down, it might tell us that it's broken down over 30 events, but it won't tell us how long each event is. Finally, it's not applicable to use on continuous data.